All right, good morning, everybody. Thank you very much for being here. Thank you very much to the organizers for organizing this, for inviting me, to the CERM for hosting us. So far, it's been a great conference. All right. Okay. So, Bram just said that we're supposed to make this sort of a broad audience talk and that the speakers have been told many times. This is the first I'm hearing about it, but okay, so. Okay, what I want to talk to you about today is exactly the opposite of what you want to do in sort of a broad audience type talk, is talk about things that are sort of very recent and that are still mumbled in my head. So I don't have any hindsight on what I'm talking about. I will raise the board, yeah. So far I've just written crossing the line, but what I want to say is that what I'm basically going to do is, or what the sort of the recurring theme that's sort of behind this, is going in some sense from a problem for graphs to a problem on surfaces, which for many people in the audience is something that they've done, or these are trajectories that people have taken. And the trajectory I want to talk about today is maybe a little bit different. I have a question, should there be lights here? Or?
Yes, if you ask me gently.
Okay, I was just, yeah. Okay, great. All right, so I want to start off with something that I just learned about recently, and I learned it from my co-author, so everything I'm going to be talking about is joint with Alfredo Hubbard, whose name doesn't look difficult to spell, but if you work in Teilchenbühler theory and you write Hubbard, it's very difficult not to put two B's. Okay, but that's just a side note. And the starting point is, let's say, story number one, is what's known as the crossing lemma. Okay, and the crossing lemma is a lemma for simple graphs and you assume that your simple graph has n vertices and m edges. All right, so this is our starting point. And the assumption is that the number of edges is larger than the number of vertices. Okay, so I mean, there's different assumptions you can make here. I'm gonna write down one like this. So the number of edges is larger than 4 times the number of vertices. And what the crossing lemma says is that, well, when you try to draw this graph in the plane, no matter how you draw it, you create intersection points in the drawing. All right, this is called the crossing number of the graph. So you try to draw the graph in the plane, and so you draw G in the plane with as few crossings as possible. Okay, and the lemma says that this crossing number, so this is the minimal number of crossings of a drawing in the plane, has to be bigger than, okay, some constant times m cubed divided by n squared. Okay, for some positive constant.
This is not necessarily straight lines.
Not necessarily straight lines. No. But you're already hitting at the heart of the problem here, so that's very good. Excellent. All right, so this is what the crossing lemma says, and it's due to a bunch of people whose name I will just diligently copy on the board. From the beginning of in the beginning of the 80s, there's a lot of names, so those of you who still have some sleep to catch up, please go ahead. So that's one team, and independently another team is just one person, latent. Okay. And let me tell you why it's true, because, I learned about it recently, so let me tell you why it's true. All right, so if G was planar, okay, if you had a planar graph, all right, you'd have a definite condition on how edges, number of edges and number of vertices. Okay, so you'd have a condition which is that m would have to be less or equal to 3 times n minus 6. Okay, and this basically comes down to Euler's formula. When you look at a planar drawing of the graph, you can triangulate all the remaining zones, you do a computation, and this inequality comes out. Okay, so from this, it's not so difficult to deduce that if G is not planar, then the crossing number of G, and this is going to be true for any graph, has to be greater than whatever the difference is between these quantities. Every time you add an edge, you have to create at least one crossing. Okay, so what that means is that the crossing number has to be greater or equal to m minus 3n plus 6. All right? And so, all right, so you would say, this is not what I'm trying to prove, which is true. This is not what I'm trying to prove. But using this, we can prove this much stronger inequality here. Right? And here's the argument. That one's just going to go on forever. There we go. Okay. And so here's the argument, which is very elegant. So you take a drawing of G. So you choose your favorite drawing of G with some minimal number of crossings. And then what you do is you look at subgraphs that you get by choosing vertices randomly with respect to some number. So more precisely, you fix P somewhere in between 0 and 1. Okay, and then what you do is you choose every vertex of your drawing with probability P. Okay, so you get a subgraph, choose each vertex with probability P. Okay, and you get a subgraph which I'll call HP, because my name is Hugo Parlier. No, okay, sorry. Okay, so you get a random subgraph like this. Okay, and then you look at what happens. So, of course, for this random subgraph, it's also a subgraph. So its crossing number behaves exactly like our other one. Right? And so I get exactly that this is going to be greater or equal to, how do I want to write this? The number of edges of this subgraph, right, minus 3 times n, the number of vertices of this subgraph, right, plus 6. We're going to stop worrying about the 6 in just a second, but nonetheless. So this is true, right? And now I can look at this and I can take expectations. Right? So by taking expectations, what do I get? So I look at these different values here. Right? So of course a vertex, you're choosing it with probability P. Right? So this becomes minus 3 times P times the the original number of vertices we had, right, which was n. Let me just make sure I get this right. The plus 6 doesn't change. The number of edges is p squared. If I had an edge, then there's a chance that I have that edge with p squared. Right? So this becomes p squared times m. And then the crossing number, if you think about this, so you're seeing a crossing number. So it's a simple graph, right? So if you look at the crossing here, this is your crossing number. There were vertices associated to this. Right? The crossing number appears with probability, I mean, this becomes P4, right? So this becomes P4 times the crossing number of my original graph, G.
Okay. In new subgraphs, maybe because there are less edges, you can do a better drawing than this one.
This is true, but I'm looking at what I'm seeing. Right? Right? This is true, but I'm looking at exactly what I'm seeing. Yeah, that's right. Yeah. Okay. And so the thing is that I have this inequality that's going to hold for any p, and I can choose now the p any way I want. Okay? And so here's a good choice. Let me put this up here. Whoops. And now I realize that my order of backboards was completely wrong. Great. Okay, so I'm just going to go here. Can people still read on this side? Okay. And now I want to choose p to be equal to, all right, so, whoops, was that me? Probably. Okay, so there's different choices, but I want to choose p to be equal to some constant times n divided by m. Okay, so there's different choices I can make for this constant. But the point is, when I do this, what I engineer this thing here. In fact, you can take, if you want, you can take c to be equal to 4. That's one possibility, right? So that this thing is actually, because yeah, it's probably a good idea, because I took m greater than 4n, so then I want this to be less than 1. Take equal to 4, and you work out the algebra, and what this becomes is that the crossing number of g becomes greater or equal to, and then you just work out the algebra here, and you get 1 over 64 times m cubed divided by n squared. And you can choose different constants c, try to optimize this in a better way. Then you have to put some other condition on your number of vertices compared to your number of edges, and so on and so forth. So there's different optimizations you can do here, right? But all in all, they're always going to give you some positive constant times m cubed divided by n squared, right? And there's different refinements of this. Okay. Very good. So I want to point something out, is that this inequality, so of course when I was told this inequality, I misread it completely, right? And I'll tell you how I misread this inequality completely. And you'll see why I misread this inequality completely. But in particular, I want to point out that the m satisfies certain conditions. So the m has to be greater than, as we pointed out, some constant for this or any type of inequality like this. M has to be greater than some constant times n, but it also has to be less than n squared divided by 2, right? Because it's a simple graph, right? So this inequality only works for certain regimes of m compared to n. Right? Once you have n, you can't let m go to infinity, right, for fixed n. And all right, so that's one thing. The other thing I want to point out is that the simplicity, of course, is essential here. Because otherwise, if my graph was not simple, well, here's a graph with many, many edges. It has 5 edges, which is a lot, right? And there's no crossings whatsoever, right? And of course, you can do this for any number. So simplicity, of course, is absolutely essential in this lemma. All right, so that's story number 1. Okay, so I'm going to bring this down and try to get my blackboard order better. Well, maybe I'll leave this one up and I'll do my blackboard order here. Okay, I'm undecided as to what I should do. Here we go. Up. So my trick is I erase this blackboard and then I'm not going to use it. Okay, there we go. All right, so this is the second storyline. Right? And at least you can understand how the first storyline inspires the second storyline. And the question is now completely different. So we take a surface. Okay, and throughout my talk, my surfaces will be orientable, finite type, negative Euler characteristic. So, I mean, basically they look like something like this. Right, something like this, or something of this form. And you ask the following question. Okay, so take a collection of M curves and I'll give you adjectives in just a second, but M curves on this surface sigma. Right, so that's your setup. That's very curious. Ah, no, it's not. I feel like I'm like driving like an American driving a stick shift or something. I've been in cars with this. It's great. Okay, anyways, take a collection of M curves on sigma, and then the question is how many intersection points do these curves necessarily create? All right. So let's put some adjectives on here so that this actually makes sense, and you can put your choice of adjectives. So there's a first thing that I want to say, so I'm going to put the adjectives over here. Let's start off with simple curves. All right, so simple closed curves. Okay, and to curves, I'm asking that they be non-homotopic. And for exactly the same reason that I did that drawing there, if I don't require anything about homotopy classes, then the answer is going to be 0. Okay, so, all right, so this is the question. So I'll let you think about that for a minute, or 5 seconds, and I'll tell you the answer. Okay, there we go. Okay, and I'll tell you the answer over here. So this is the first of our results that I want to tell you about. And it's exactly in this context. So you take M simple curves, you have an orientable surface, negative Euler characteristic, and for this result, I want to take a surface that has a certain amount. So let sigma have curve complexity kappa. All right, let me try to draw a reasonable kappa. Okay, and what I mean by curve complexity is the following thing. So the curve complexity, here is the curve complexity. It's the number of curves in a Pants decomposition. Okay, so example. If I take a genus 2 surface, right, the number of curves I need to make a Pants decomposition is 3. Okay, the complexity here is equal to 3. If I have a torus with one boundary, then how many curves do I need to break this down into Pants? So Pants are 3-hold spheres. I need exactly 1 curve. So in this case, the complexity is equal to 1. Right? Does that make sense? Okay. And so we have a surface with curve complexity kappa. And then the result is, so what is our result? All right, so there exists a constant that depends on the topology of the surface that's positive, such that right, a collection of M curves, okay, and I'm going to call this collection gamma, right? This is the collection of M curves. This is the union of all these curves. Satisfies that the crossing number of this, so by crossing number of this, I mean the number of intersections that I see, that the minimal number of intersections that I get from these curves has to be greater or equal to this constant times m to the power of 2 plus 1 over 2 times kappa. Okay, and this has to be for large enough n, for large enough m. All right, so this is very different from, at the basis, this is very different from the crossing lemma, because what we're thinking of, we're thinking of a fixed topology and very large m. Right? So we let the m go to infinity, and we want to know how many intersections do we start to see as m goes to infinity. Right? So this is exactly the picture I had in mind when Alfredo told me about that. And so I thought he was saying something like this. Right? Yeah, the main difference here is the non-homotopic, exactly. So you can interpolate between this problem and that problem, which is something I want to do for you. I want to show you how you can get from one problem to the other problem, at least at the, the human level or whatever.
With the quantifiers, why can't you absorb the constant? Why can't you get rid of the large enough m by absorbing it as a constant?
Oh, you can, yeah.
You can give some actual constant.
Yeah, I mean, if you were really motivated, you could, yeah. Yeah, exactly. Yeah, you can. There is actually a reason that I'm letting the m, I want to say for large enough m, and that's because I want to be a little bit lazy at one point and use asymptotic results. That's why. But if you want to break it down and actually get for the smaller m, yeah. There's another reason for that is that these problems, they tend to have different behaviors at different regimes. Right? So for m that's relatively close to the topology in some sense, you might expect some behavior, and these questions are all kind of interesting, right? Okay. All right, so this is sort of what happened to me, is that when somebody starts doing this board, right? They start drawing this on the board, and so this is like, okay, this is a drawing like that. In my mind, what happens is I see things like this. So it all starts the same, but then I start going like this. And people are like, what are you doing? I'm like, yeah, no, that's right, that's fine. And then I'll have something like this, and then I'll go around again, and then I'll start doing this, and right. So this is sort of, this viewed from the point of view of a topologist kind of looks like this, right? And you want to say, okay, no, but that's fine. We can just keep adding lots of edges, and we let the number of edges go to, and you're like, no, you're not allowed to do that. This is a simple graph. I'm like, well, simple. These are all simple arcs. That's fine, right? And this is sort of what happens in your mind. And the thing is that here's sort of a related problem. Like you get immediately from the crossing lemma to something that looks like this by looking at sort of a related problem, which would be take n points in the plane, which of course from a topologist's point of view is if you're going to take n points from a plane, you might as well just say that you took n plus 1 points from a sphere, right? Take n points off a sphere, or on a sphere. And so now you have n points on a sphere. And now you start looking at arcs, maybe simple arcs, on the sphere. And you ask the same question. Right? Take n points on a sphere and look at arcs. Okay. And again, the arcs you need to have adjectives that are associated to this. You can take the arcs that are simple if you want. Right? This is possible. Or you could take the arcs that are not necessarily simple. But to be able to look at many arcs, you have to take them non-homotopic, pairwise non-homotopic. And if you look at what we proved here, you also get an answer to this. Right? So this also gives you an answer to this problem. And so sort of a corollary of this, that if I have a collection of arcs, right, of cardinality with m of them, then the crossing number of this thing here is also superior or equal to some constant times m to the power of 2 plus 1 over 2 kappa. The same, exactly the same.
This is on the sphere or on a general?
Yeah. So this could be on a sphere with n punctures.
On the sphere, they're all homotopic.
No. So these are punctures. So exactly. So like on my drawing, these ones here are all, the points are fixed, yeah. So you're looking at homotopies, but the homotopies aren't allowed to cross the points. Right? And so here with this, and then you have something like this. Right? But the condition on the underlying surface is not that it's a punctured sphere, it's just that there is at least one puncture. Right? You need one marked point for this to work. Right? This is all you need. And why? Why do you get this from this? So why? And well, the short answer is that if I look at an arc that goes from here to here, I can get a curve from that arc just by replacing it by something that looks like this. And now if I have two arcs that intersect, of course my drawing is sort of not generic in any way, but every intersection between 2 points on the arc corresponds to 4 intersection points on the curve. And because I'm being lazy about constants anyways, then that's fine. And so here I have 1 point, and then here I have 4 points. Okay, so 1, 2, 4 in intersection points. Okay. But in fact, I mean, that's not so much the point of view that we really want to take, because you can also prove this result directly using the same methods that you can prove with the other one. And so that's just to sort of say why these things are related. And the other thing is that from a topologist's point of view, when you look at simple arcs on a punctured surface, this is often exactly the baby case, or the baby case. It's not necessarily any easier, but it's from simple arcs, you automatically think of simple curves. And that's one of the reasons how these things are related. And so this is sort of how you get from one problem to the other, right? By just misinterpreting the crossing lemma and then getting from one problem to another. Okay. So let me tell you how some of these things work. Okay, so let me try to solve the impossible problem of these blackboards. Okay. Yeah?
So like you can interpret your corollary as like a different inequality for the crossing lemma. Which one is better, yours or the previous one?
Well, it depends on what you mean. So the inequality that we have works for m going to infinity and n fixed.
Okay.
So this is really the main point, is that they're not actually related in some sense. Because what I'm talking about is the asymptotics as m goes to infinity. Whereas the crossing lemma, you really cannot do that. You can never get beyond n squared. Right? So the answer is that, in fact, they're not related. I mean, there's clearly a larger picture in which they all fit. Right? I mean, many of us here are doing, or many of us have thought about random surfaces of different types, right? And this is not so different from that at the philosophical level, is that when you start looking at a random surface but you fix the topology, it's very different from when you start looking at a bunch of triangles and randomly gluing them together, then the topology is growing at the same time. Right? And so the crossing lemma is more in the, we take a bunch of triangles and we glue them together and we let them grow. Whereas this is more, we fix the topology and we let the m go to infinity, right? So that's the, maybe one sort of analogy with this.
Do you want an answer to the question of drawing graphs on these surfaces? It's not the same.
It's not the same. Well, sorry, what do you mean?
Crossing lemma,
Yeah,
instead of the plane, put any surface.
right.
So this is not an answer to that.
This is not an answer to that, no. This is more, you fix a surface and you let the m go to infinity, absolutely. Yeah, so that's another example. Like you want to have specific crossing lemma results for fixed surfaces, and then, but yeah, absolutely. Yeah. So you replace the plane with another surface. Right, exactly. Yeah. Yeah, there's bucket loads of results. There are bucket loads of results about crossing lemmas in different regimes. Okay. All right, so I want to talk about one essential ingredient. And the essential ingredient that I want to talk about has to do with hyperbolic surfaces. Okay. And in the world of hyperbolic surfaces, so this time we're not looking just at a topological surface, but an actual hyperbolic surface, which these are surfaces that are locally look like the hyperbolic plane. Right? So you somewhere in the hyperbolic plane, geodesics look something like this, and you get sort of a similar picture on your surface. So you have a hyperbolic metric on these surfaces. Alternatively, you can construct these surfaces by taking polygons and gluing them together. So you take your favorite polygon in the hyperbolic plane, and you paste it together using isometries you associate to different sides different isometries, so now you're in the hyperbolic plane, and what you get is a hyperbolic surface. Okay. All right, I can talk for, probably months about this if people want to know more, but let me know. But if something is not clear, just let me know. Okay, so we have a hyperbolic surface. It satisfies all the properties of our original surfaces. It's finite type. It has curve complexity kappa, and so on and so forth. And there's a famous theorem of Mario Mirzakhani that in fact counts simple closed curves. So one fascinating fact about hyperbolic surfaces that if you've never seen before is the one thing to retain from this talk, besides the fact that I don't know how to use this microphone, and that is that when you look at a free homotopy class of simple closed curve, or closed curve in general, there is a unique geodesic in this homotopy class. So the negative curvature you can sort of see on this picture, because it's curved one way this way and the other way, implies that in a free homotopy class, there's a unique closed geodesic. So counting simple closed geodesics amounts to counting homotopy classes of simple closed curves. Okay, and one of Mirzakhani's famous results is that for X hyperbolic, the number of simple closed geodesics of length less or equal to L, so you look at all the simple closed geodesics of length less or equal to L, divided by L to the power of 2 kappa. Okay, and then what you want is to say that there exists a positive constant that you associate to this surface. You divide this, you take the limit as L goes to infinity, and this is equal to this positive constant. Right, so this is her famous curve growth result. And I won't be able to talk about this later, but I was planning on talking about this later, is that this is very different from if you looked at all closed geodesics on a hyperbolic surface, where then the growth is exponential. So this is a very particular thing about simple closed geodesics, so curves that don't self-intersect. So they have polynomial growth. Let me give you another version. There's many generalizations, but here's one that I actually need. So there's a sort of a topological generalization of this. Which we proved together with Viveka Erlandson and Juan Soto, which is the following version of this. And let me just, so how am I going to do this? Let me set it up over here. So something more basic than looking at a hyperbolic metric is you can look at a polygon. So this is just a topological polygon. And you have side pairings. And you suppose that this gives a surface sigma with your side pairings, which has curve complexity kappa still. So this is just a topological setup, and this is your polygon P. And instead of measuring lengths using hyperbolic geometry, which is sort of complicated, right, you can measure lengths in a much simpler way, which is just the number of times it intersects your polygon. All right, so if I have alpha, a simple closed curve, I determine the length of alpha. This combinatorial length is its number of intersections with the polygon. Right? And of course, when I say the length is, I take alpha is a homotopy class of simple closed curve, and I look at the representative that intersects this minimally, and I ask that I don't go through the vertices. Okay, so this is what I mean. And this is a way of looking at the length. Does this make sense? So I have a simple closed curve, and I try all drawings, and I try to minimize the number of times it intersects the polygon. You look confused, so, yeah? Okay. Do you always look confused? Okay, very good. It's good to know. I mean, we just met, so. Okay, very good. All right, and so the result is that you get the same theorem. Okay, so there exists a constant that depends on P, the polygon, such that this is true. The limit as L goes to infinity. I don't know what it is that I do to make that, but anyways, I think it has to do with erasing the board, but okay. L to the power of 2 kappa, and the number, the limit of this is also equal to this CP. Right? So it's sort of a combinatorial version of this other theorem. Okay.
This does not depend on the length, the Riemannian length. Is it just
I mean, yeah, this is not hyperbolic. This is the length is by definition the intersection with the polygon.
completely topological?
It's completely topological, yeah. It's completely topological. So you could do the same theorem holds if you replace the surface with a Riemannian metric, and you look at the length as being the minimal Riemannian length in the homotopy class, then the same theorem holds.
This theorem implies Riemannian?
No. Well, I mean, it does. The one I've just told you does imply Merriam's theorem, but you have to, it's more complicated than that because in our first proof, we need Merriam's theorem to be able to prove it. So this is, in the meanwhile, there's proofs that don't involve Merriam's theorem, but anyways. Okay, so I just want to tell you how these two things sort of relate and how you get from curve counting to intersection, which sounds like it's not the right, it doesn't seem in any way how these problems are related. I mean, at least not. Well, of course, to me, it should, say something, but, okay. So it can't do two things at the same time. See, if you try to do, no. So basically what I'm going to tell you in the remaining 5 minutes is how you get from one. So this is sort of the sketch proof. This will not even be close to proof, but I want to just tell you what one of the ideas that sort of comes into this. And so I take gamma, my collection. So by now we've forgotten what gamma is. So it's a collection of M curves. Okay. So we take gamma, this collection of M curves, and we split them into filling sets. Okay. So what do I mean by filling set? This means that the curves, a set curves fill a sub or a surface if the complementary region or regions have no topology. Okay, I'm being a little bit sketchy because depending on if you have boundary, then, so I'll just give you an example. If I'm in genus, then here's an example of a filling set. I take this curve, this curve, this curve, this curve, and this curve, and they fill, because if I cut along them, then what I get is two polygons. Right? And so these are simply connected. Okay, but I want to be careful a little bit about what I mean, because maybe my surfaces have boundary, and if I have something like this, I'm not going to be able to break it down into a set of polygons. So this example, these two curves fill. Right? So these are examples of filling sets on these two different types of surfaces. So the important thing is that if I do this in a reasonably smart way, then I break it up, I break my collection gamma into filling sets, and each filling set has a number of curves in it that only depends on the topology of the surface. So think of it this way. I look at my curves, I take a curve randomly, I put it in the set. Now I look for another curve that fills a larger subsurface than my first curve. I add it into the set until the subsurface that's spanned by these curves becomes larger and larger. Okay? And at one point I have to stop because I have many, many, many curves and very, very, very little topology. Right? So I have many curves, little topology. At one point I have to stop, and then I go to the next set. I throw these curves away, and then I go to the next set. I take a curve, I add another one, and so on and so forth. So what I get is gamma 1 to gamma some constant times m, and I'm being a little bit cheeky here, filling sets. In fact, I'm being very cheeky because it could very well be that all of my curves live in exactly one small part of the surface. Okay, so I'm being cheekier than cheeky, which is not necessarily the cheekiest, but definitely very cheeky. And so just bear with me and pretend that everything's going really as planned, okay? And I have this collection of filling sets, and the key thing is now I take one of them. I take one of these filling sets. And so one of these filling sets right, in polygons I tend to draw such that they look hyperbolic, and that's just because that's the way I was. And I take these polygons, and what I do is I can paste them together to create a single polygon. Okay. And I paste them together to create a single polygon. Now this single polygon might be huge, right? It might be absolutely immense. But in some sense, I can sort of modify it to get something that's more like a standard polygon. Which again, I'm P, because P for polygon. There we go. All right. And so here again, I'm being a little bit cheeky, but the point is that I can break this down. I take this filling set, and I construct a standard polygon for my surface from this filling set. And the point is, the reason I have this polygon is that the intersection with this polygon, I'm going to denote it pi, the intersection between a curve and this polygon is going to be greater or equal than the intersection of this curve with my filling set. This is the key property that I want. And with this in mind, I can now count curves. So I have that number of filling sets. Now I look at all the curves that are not in my chosen filling set. Right? So I had my m curves. I removed a filling set, which is not very big, and I still have roughly m curves. And this counting result tells me that if I want to construct m curves, I'm going to need to intersect this polygon a lot. So I still have m curves. They're going to have to intersect this polygon a lot. So what that means is that these m here, the remainder of the curves, they give roughly, and this is where you have to retro-engineer this inequality here, So if I'm cheating and I say that I need that the number of curves is equal to L to the power of 2 kappa, right, times a constant, then this here is m is equal to a constant times L to the power of 2 kappa. And that means that if I do this backwards, that means that L is equal to, right, 1 over some other constant, and then m to the power of 1 over 2 kappa. Right? I've just inversed this equality, which is not an equality, but you can sort of gather that from this, right? And so that means that these m curves, they generate, well, there's m of them, and they have to generate sort of on average this number of intersections. So this gives us m times m to the power of 1 over 2 kappa intersections. So just the curves with this original filling set, they have to intersect this filling set m times m to the power of 1 over 2 kappa intersections. And I have m filling sets, so this is true for each of them, and I've only double counted. I've counted every intersection twice, but I haven't done more than double counting. And so I put that together, and this gives m times m times m to the power of 1 over 2 kappa intersections, which is, of course, is equal to m plus 1 plus 2 kappa. Yeah?
I didn't follow the point where the number of curves has to be to the 2k. How
Yeah.
do you use the non-homotopic, the fact that they are non-homotopic to relate to this to the 2k?
Well, so what this says is that asymptotically, the number of curves, that these are homotopy classes of curves that intersect my polygon, grows asymptotically like L to the power of 2k. Yeah. I mean, to make this actually work, you have to, of course, work a little bit harder than just say, oh, those look the same. Let's do that. But roughly, that's the idea. All right, and so this gives us m to the power of 2 plus 1 over 2 kappa curves. All right, let me just end by saying two things. The first thing, I mean, I really just say two things, but the first thing is that you can use a hyperbolic surface, any hyperbolic surface, well, not any hyperbolic surface, a well-chosen hyperbolic surface to show that you can find of m curves that intersect at most m to the power of 2 plus 1 over kappa. All right, so you can get reasonably close to the lower bound by an upper bound. And the second thing I want to say is that there's a whole other batch of questions that are really interesting that happen when you relax the condition on simplicity. And for those who are interested, I'm happy to tell them more, but thank you very much for your time.